Afternoon mga Bisaya. So, I posted this question like 2 weeks ago, and I really had an interesting discussion with another engineer. He commented on this one, and then I was confused at first with his comment. So I responded, and it started our long, like really long discussion with regards to reinforcement in foundation. So first, I asked this question because my um, next topic or next video was about foundation. So I posted this like some kind of a question. Um, so basically, the question is ahead of our lecture series about foundation. Is it possible to have a footing without reinforcement? Because I was going to discuss. My plan was to discuss um, based on my experience because I did a lot of um, retrofit for foundations and like basement foundations for residential buildings. And then most of the um, what do you call this one? Most of the reason why um, we have all these foundational retrofits because in the prescriptive guideline there is a um, like some kind of a table, and then at the same time for the wall, and like what how much reinforcement you need, and then in the foundation, as long as the thickness or the cantilevered portion, I will discuss that later in detail, but so that was in my mind, like basically as a preparation for that discussion. So I posted this question. So the question was this one, and then this. So um, what's his name? So I just I took a screenshot of our like initial discussion. So he said, so he responded, yes, but you have to compensate the loss of reinforcement through a very large increase in concrete dimensions, mainly its thickness. The thickness increase should be designed to withstand the punching shear caused by the column that reason. So my confusion started when he said to compensate the loss of reinforcement. But um, in practice, so I responded like in practice, rebars in footing are not considered to resist punching. In fact, you have to check punching first to determine thickness before you determine the rebars. So as we all know, the procedure for in designing footing, for example, is first. So you have the bearing. So you have the bearing capacity, right? Say, shall we say, for the sake of discussion, 100 kPa, and now your load is a 100 kilonewton, just for the sake of discussion. So first, when you design the footing, you have the load, you have the bearing capacity is one. First is determine the area, which is length times width. So all you have to do is divide the load by the bearing capacity. So you have now the area. Now, next check for that one is I will say 2A and 2B. This is the direct shear or the one-way shear. And then the second way is punching, right? Punching shear or two-way shear. Now, in this step, all you have to so you already have the dimension, right? So this time you will check the thickness. So you will design the thickness, right? Depending which govern between direct shear and the punching shear. So now you have the area, and then you have the thickness. So once you determine this area and the dimensions and the thickness, that's the time you check for or design it for bending, right? So step three is bending. That is where you get your rebars. Now, that's why I was confused with his comment because he said you it will you have to compensate the loss of reinforcement. And I don't like I was confused. Like in practice, this is what you do, right? Determine the area, then check for thickness. So you already design for thickness even before you design for reinforcement. So why would you compensate the loss of reinforcement when in the procedure you have to check the thickness first to meet the punching, you know, the punching shear or the direct shear requirements before you design the bending. Now, so he said, like, um, so basically this was our like first um, like exchange of ideas. So I told him like rebars has nothing to do with punching in footing analysis in practice, although in theory it has. Well, like, of course, so once you have the rebar, but like I said, in practice we don't consider the reverse for punching, but it has something like or it has like in theory it will help, but we just neglect that part in designing the foundation. It's the same as if you design, for example, like if you have a flat plate, all you have to do is you will just add reinforcement to resist the shear because, for example, if this is like your column, this is your footing, this is your like punching shear plane. Now, if you have rebars here, it will cut through the rebar, right? So in theory, it still helps with the punching, but in practice, we don't do that. We'll just check the full capacity or full resistance for punching, relying on the capacity of the concrete itself without any reinforcement. So you use the formula that one. So um that's why I was confused with his comment. And then he like in further discussion he mentioned about that the bending is initial failure. He's talking about initial failure and then the final the ultimate failure. So he said uh so this is his um answer or respond to my. I mean, if you are curious like regarding our discussion, you can check that post. But I only took like screenshots of some of the important points that he raised. So he said it's just a chain of reaction of structural failures. Once bending occurs, it may break off the footing segment, which once segments break off, there's now less footing area. And I told him like I understand this sequence, like no question. Not like basically what he meant was so if this is your footing, right? If this is your footing and this is your column, and then you have the rebars here. Now, if this, for example, this is your shear, right? Shear plane. So this is where you need the rebars because this is now the uh how do I call this one? Outside the influence of the like this shear plane here. So that's why in what chapter is that in ECI that as long as this length here right, is equal or less than the the depth, no, then you don't need a reinforcement because this is now in compression. Even in the ECI code, um, under the plain concrete, you don't need reinforcement as long as the element is always in compression. So this is what I'm trying to arrive at when I posted that question, because I will be discussing about footing and also underlying foundation. The same situation. But again, like his comment about that sequence, this is what he meant. Like if we have failure, if this failed, if this footing failed in bending, if we don't have reinforcement, it will reduce it will reduce the effective area now, because you have this already failed and then it cracks, you know. So you now have reduced effective big area. Now, once that happens, you will now have a bigger bearing pressure now, because you are like the footing area is reduced. Now, if that's the case, then your shear force right here will increase. So that's his point. Now I get this um, sequence. No question about this one. But my point was, if you have a column or a wall footing, and then this is your wall or column, and then if this influence line, I would say, if this one, or even if you really have a thick, if you have a thick footing, what will happen is this one will follow the regardless of your thickness, it's always the same at that slope. Now, if this, I would say, influence line, like this one here, if that one is, if this exceeds the width of the footing, or if this portion, like the cantilever portion, this one, say L, if this L is less than the depth, this one will, what will happen, or what will happen to the failure, or the shear plane. That means this footing will always be subjected to compression. Now, unless there's an uplift on your footing, then that's another story. But if this is always subjected to compression, then technically you don't need reinforcing bars here, because it's always in compression. The same if you have a like an underlying foundation, you have pile or build pile, as we commonly call it. So this is what it looks like for build pile. Now, the reinforcement for underlying foundation or build pile, that's the only reinforcing bars. And sometimes this pile, this vertical column, doesn't even re- um, reach the bottom of the pile. Sometimes you have, say, for example, this is 30 feet, right? Some engineers will design like pile only up to, say, 20 feet, and then this one is no longer reinforced, which is fine. I've seen this many times with other designs, but personally, I don't do that one. I always have reinforcing bars all the way down. But this part, this is not reinforced. This one, that one. So all you have to do is, so you design the build area based on the bearing and capacity and the load. So you will have now the assumed uniform pressure here. Now this will shade off right here, right? With this load. Now, as long as this thickness is designed to resist the punching, you don't need reinforcement. So this is what I'm trying to um or what I had in mind when I posted that question, that you don't need reinforcement here. The same with footing. As long as this is always in compression, you don't need reverse. The only um or the confusion starts when he said um to compensate the reinforcement, and then his like the bending is the initial failure, and then um what we call this one, the punching is the ultimate and like failure. And I never, like, to be honest, I've never heard or I never read something like that in any literature that I read. So that's why I asked him, because that's what I always do if I if I see like a um comments that is I would say not against, but I'm not familiar with, or even like I read something that I'm not familiar with in like in Facebook, I will always research, like, I mean, to at least if there's something um if there's like new innovation or whatever it was, I mean, at least I will know. And I always do that. I always search, like, maybe at least I will like by reading I will learn something, right? So I asked him, like, do you have any literature that I can read, at least, because it really interests me what he said. And well, at first he said um he searched AI. Well, disclaimer, I don't at this time I don't really trust AI, because what AI does is it will just gather, you know, all available information, even if it's wrong. It could be a Facebook post or any, forum or any literate or discussion. It will compile all the um, information. And that's why sometimes, like, I don't know if you've tried, but we've tried this in the office, that if you just twist the or change the, like, rephrase the question, it will sometimes it will answer or arrive at a, like, it will show you all the information which is completely opposite of what you've searched earlier with the first question. So he said, like, try using this exact phrase. I haven't tried, but yeah, we can. And then he mentioned a book also by um, or I think I did not screenshot, but he mentioned a book. And then I searched the book. It reference to ECI also. And then in ECI, I I don't know. I mean, maybe I missed something, but I'm not familiar with the recent provisions of the ACI, because I always, or like the last time I read, like, or the I think it's ASI 7 or ACI 318. I think zero. I can't remember the last, because I was still working in the outsourcing company in 2009, and then the last IBC code that I used was 2006, and then ACI 08, I think. Can't remember the, but I, like, over that period, I've never read something like, initial failure is binding, and then the ultimate failure is shear. So I was really interested. I was curious, and I asked him about what literature he read, so I can read about it. And then he mentioned a book, and then I look at the book, and well, I told him in my comment, like, if it's not that expensive, then I will for sure buy that book. And then when I look at it in Amazon, and then in Amazon, sometimes you can see the, like, some kind of, sometimes it will show the table of contents, or it will have some kind of like a like an introduction, and then it refers to ACI 318, and then he said like if you search also, let's try this one because I've never so he said use the exact can binding stress and binding stress can binding stress result to punching shear and footing. Okay. Study can binding stress result to punching shear and footing. I don't think this is. Oh, let's try Google. So this is what he searched in AI. So he said can result in his bending stress is specifically in the form of unbalanced movements can result in or significantly increased punching shear and faulting, while punching shear is primarily caused by vertical horizontal load. Bending moments transferred from the column to the faulting create additional uneven shear. This is different because what it means is so you have unbalanced movement. So break failure, shear higher one column. No, this is different. This is, I mean, it doesn't say that the binding compensate. Um, I get this. I think what this I don't know if this is exactly that's the problem with um AI. If you say let's try is instead of can I will replace it binding. Let's see if it will show the same information. So the science, this the same science direct and balance moment two-way action. Now there's another information here, two-way action, which is not shown in the first one. So this is what I meant by or when I say I don't really trust AI this time because once you change a single word, like rephrase the question, it will show a different. At least this one it shows the unbalanced moment, but this one it was never in the first um like the two-way action punching shear. So this unbalanced moment, what it does is, so for example, where's the, so if this is the footing, right, and this is the column. Now, if it is pure axial, like compression only, so you will have a uniform, uniform bearing, right? But once you introduce a moment, for example, in that direction, so there will be a minimum and a maximum pressure. So most likely it will be like that one. Now, if you design the punching shear, or if you check the punching shear based on this uniform load, now that is um not accurate because once you increase this one, see, you will notice that you have a trapezoidal pressure here, which is way higher than your balance load. That's why it says like unbalanced movement because that movement, this extra low bearing pressure here because of this movement in this direction, it will increase the pressure at this and this one on this side. That's fine. It's lesser, but on this side here, it increases the bearing pressure because of that moment. That's why in your bearing check, you have to get the maximum, Q max, which is equal to um, P over A plus minus M over S, right? So this plus will give you the maximum, and then the minus will give you the minimum, and then you will have that, middle third. The resultant has to be in the middle third so that there is no uplift going on. Because sometimes if the footing is small and then the bending is large, what will happen is um there's a chance that the bearing pressure will be like this one, right? There will be a net uplift here, which is really not effective. And most software, once your resultant is outside the middle third, it will just not run, or it will not run. Like some software, for example, like ASDIC footing, it will not allow you to proceed with the calculation once push it up ASDIC. Yeah, like I said, some software, once your resultant is outside the middle third, then it will not proceed with the calculation. You have to adjust the dimensions. So of course, in this scenario, you have to design the thickness of the footing so that it will resist. It has enough capacity to resist the increase in bearing pressure. So that's what this one here. And I have no question about that one. My only concern, or my what confuses me, was his first comment that he said, like, you have to compensate the loss of reinforcement, and then it will have a, like, ridiculous. He says here, like, um as long as you increase the thickness of the footing by a ridiculous amount of, like, to account for the punching shear, your point was on bending, which is correct. Since that's the initial failure and the damage compounds, it ultimately leads to punching shear. So that's the part that I don't really understand, and I'm trying to find, like, information, or if you know something, just let me know because I'm really interested. Like I said, I've never encountered such statement in any literature that I read, and I'm really interested to see, like, what exactly was, or how it was worded or something. And like, I just don't understand why you need a ridiculous amount, to account for the punching, when in the design of foundation, you do the shear check first before the rebars, right? Because sometimes you don't need, like I said, in this example, you don't need rebars here. You don't put rebars in build pile. Of course, how can you do that? But all you have to do is make sure this is thick enough, this one, right? And then whatever's the angle, so that this length here, when you check for the punching shear, that's more than enough to resist the bearing, the bearing or the shear due to the bearing here of the at the base of the pile. And the same with wall footing, you know. Now, if your footing is wide, of course, if this is wide and then this no longer, this is already outside the influence line for the shear, then this part here, of course, you need reinforcement if this exceeds the depth. That's why um, I also posted this in one of um, the post. I don't know if you remember, where basically what they did is, this is the footing for the column, but their footing is trapezoidal, something like that one. So this is the same as the build pile. This is just for footing, but theoretically it's exactly the same what a build pile is. So as long as you have enough thickness here to resist the, to resist the punching shear, and then these lines, usually this one follows the the slope also of the shear plane. Now, if this one here, you know, if this line at the base, if this portion is shorter than the projection of this line, then you don't need reinforcement. Like technically, you don't need reinforcement, but still you have to provide temperature bars. But for an isolated footing, um, shrinkage, I don't think shrinkage would be an issue if you only have like even wall footing. You don't need temperature bars for wall footing, but you know in practice we just put minimum, but technically you don't need one as long as it's like I say, always in compression. And then the idea with footing not having a temperature bar is because, so if this is a wall footing, right? If that is a wall footing, if this is a wall footing, your any cracks, no, there will be no cracks along this length. The cracks will be like perpendicular to your wall. That's where your crack is. But the thing is, if ever there is crack, it will always be what we call this one, um not restrained, but hold together by this wall footing. So it will never be an issue in this direction because it is always stiff because of this wall. But in this direction, that is where you have issues. But as long as like if for example, if there is a crack right here, what would be the possible um or what will happen to the foundation? Like nothing, right? Because your bending, or if it bends, it's in this direction also. Like it will not bend in this direction because it's really stiff. Even like if you consider differential settlement, it will not happen on a full thing. Like like per segment, it will happen like the entire length. That's fine. It probably tell like by how many degrees, but it will not cause any issue on the footing along this direction because it's really stiff by this one here, unless the bending is really, or your load is really large, and then this will get a really large bending on your beam. But if we are talking about wall footing, this could be what 10 foot deep basement wall or foundation wall. So it's not gonna be an issue. And then yeah, for transverse bars, like I said, as long as it is within this, it doesn't exceed this this line projected from the top of the footing down to the bottom, you don't need reinforcement here unless that one exceeds the for example, this is only this is only 10 inches, but this one is what say 48. So that means if you project this one, so this is this portion outside the outside this line, then you need reinforcement here because this will bend for sure, right? So you need reinforcement right there. So this, I mean, I don't know. I really tried to find information regarding his point, but I just can't find it. Maybe if you know something, I'm really interested to mm, learn about this one. But like I said, I've never encountered this um point, or I would say what he raised here. I've never seen this. I've never read this in any of the literatures that I read. But if you know something, then yeah, just let me know, and I will be I'm really interested on this one. I don't know. Like, I just can't understand why you would compensate the loss of reinforcement through a builder's increase in concrete dimensions. Um, Maybe it's just a misunderstanding, or I don't know. That's why I told him, like, I will just make a video of this one, like, to explain my point, because it's better that way than just right here. And then imagine how many, or it's like our exchange of comments here in my post, like what, 30 comments plus. So, and still we still not agree with each other. So I just told him, like, okay, we'll just agree to disagree at this time. And then yeah. Um anyway, so that was my point. Like, before you check for bending, you already check for punching and shear, because that's how you get the effective depth to design for the reinforcing bars, right? So I just don't get the idea, like, his point, why you have to, you know, compensate the loss of reinforcement with, large dimension of footing, and it will be, he said in his word, ridiculous amount to account for punching shear. So I don't know. I mean, if you design the footing to meet the punching shear alone, and then you just have to see to it that there is no projection here, why would you need to compensate for the loss of um rebars when you already, in the first place, you already designed for punching before you even arrive, or you even do the bending, the reinforcing bar. So anyway, um maybe there's another, or maybe one of you guys can, what do you call that one, can, you know mediate, or how do you call this one, um some kind of tiebreaker, because at this time we still don't agree with each other. But anyway, yeah, I think that's it for today. um okay, bye.